In printing, type metal refers to the metal alloys used in traditional type founding and hot metal typesetting. Lead is the main constituent of these alloys. Antimony and tin are added to make the character produced durable and tough while reducing the difference between the coefficients of expansion of the matrix and the alloy. History. Although the knowledge of casting soft metals in molds was well established before Johannes Gutenberg's time, his discovery of an alloy that was hard, durable, and would take a clear impression from the mold represents a fundamental aspect of his solution to the problem of printing with movable type. The enormous effort to create an alloy with the characteristics needed in an ideal type metal is often underestimated. Required characteristics: cheap, plentifully available as galena and easily workable. Lead has many of the ideal characteristics, but on its own it lacks the necessary hardness and does not make castings with sharp details because molten lead shrinks and sags when it cools to a solid. After much experimentation it was found that adding pewterized tin, obtained from cassiterite, improved the ability of the cast type to withstand the wear and tear of the printing process, making it tougher but not more brittle. Despite patiently trying different proportions of both metals, solving the second part of the type metal problem proved very difficult without the addition of yet a third metal, antimony. Alchemists had shown that when stibnite, an antimony sulfide ore, was heated with scrap iron, metallic antimony was produced. The type founder would typically introduce powdered stibnite and horseshoe nails into his crucible to melt lead, tin and antimony into type metal. Both the iron and the sulfides would be rejected in the process. The addition of antimony conferred the much-needed improvements in the properties of hardness, wear resistance and especially, the sharpness of reproduction of the type design, given that it has the curious property of diminishing the shrinkage of the alloy upon solidification. Composition of type metal. Type metal is an alloy of lead, tin and antimony in different proportions depending on the application, be it individual character mechanical casting for hand setting, mechanical line casting or individual character mechanical typesetting and stereo plate casting. The proportions used are in the range: lead 50–86%, antimony 11–30% and tin 3–20%. The basic characteristics of these metals are as follows. Lead equals, type of metal 10B, or 613. The basis for type metal is lead, a relatively cheap metal, that melts at 327 degrees Celsius. It is easy to handle and makes alloys with many other metals. It is, however, very soft and castings with pure lead are not sharp enough for printing. Lead is poisonous and very heavy. Lead is exceptionally soft, malleable and ductile but with little tenacity. Easily fusible with other metals, it does not produce sharply defined shapes. Tin equals, type designation 24 Snow. Tin. It promotes the fluidity of the molten alloy and makes the type tough, giving the alloy resistance to wear. It is harder, stiffer and tougher than lead. Antimony equals, type designation 623, antimony melts at 630 degrees Celsius. This highly crystalline metalloid gives type metal its hardness and a much better and sharper cast from the matrix. It has a crystalline appearance while being both brittle and fusible. When alloyed with lead, it strengthens the alloy and improves casting detail. Typical type metal proportions equals, the actual compositions differed over time. Different machines were adjusted to different alloys depending on the intended uses of the type. Printers had sometimes their own preferences about the quality of particular alloys. The Lanston Monotype Corporation in the United Kingdom had a whole range of alloys listed in their manuals. Alloys for mechanical composition. Most mechanical typesetting is divided basically into two different competing technologies, line casting and single character casting. The manuals for the monotype composition caster mention at least 5 different alloys to be used for casting, depending the purpose of the type and the work to be done with it. Although in general monotype cast type characters can be visually identified as having a square nick, there is no easy way to identify the alloy aside from an expensive chemical assay in a laboratory. Apart from this, the two monotype companies in the United States and the UK also made molds with round nicks. Type founders and printers could and did order specially designed molds to their own specifications: height, size, kind of nick, even the number of nicks could be changed. Type produced with these special molds can only be identified if the foundry or printer is known. In Switzerland, the company Metallum Pratteln AG, in Basel, had yet another list of type metal alloys. If needed, any alloy according to customer specifications could be produced. Dross equals, regeneration metal was melted into the crucible to replace lost tin and antimony through the dross. Every time type metal is remelted, tin and antimony oxidize. These oxides form on the surface of the crucible and must be removed. After stirring the molten metal, grey powder forms on the surface, the dross, needing to be skimmed. Dross contains recoverable amounts of tin and antimony. Dross must be processed at specialized companies, in order to extract the pure metals in conditions that would prevent environmental pollution and remain economically feasible. General requirements for type metal equals, type metal should produce a true and sharp cast, and reproduce the matrix in all detail. The dimensions and form should be correct after cooling down. Type metal should be strong and lasting, to endure wear and pressure while printing. Type metal should be easy to cast, this means, a reasonable low melting temperature. Iron should not dissolve in the molten metal, mold and nozzles should stay clean and easy to maintain. The molten metal should be clean, while molten it should give as little dross as possible, to prevent loss of tin and antimony. The economics have to be taken in account too. Keeping the costs down would mean, keeping the content of tin and antimony as low as possible, and maintaining a high quality of the type produced. Type metal should not adhere to the copper of the matrix. Behavior of bipolar alloys equals, pure metal melts and solidifies in a simple manner at a specific temperature. This is not the case with alloys, though we find a range of temperatures with all kinds of different events. The melting temperature of all mixtures is considerably lower than the pure components. Antimony lead mixture examples: the addition of a small amount of antimony to lead will significantly alter the alloy's behavior compared to pure lead. Although the melting point of pure antimony is 630 degrees Celsius, this mixture will be completely molten in a homogeneous fluid even at temperatures as low as 371 degrees Celsius. Letting this mixture cool, the alloy will remain liquid even through 355 degrees Celsius, the melting point of pure lead. Once the temperature reaches 291 degrees Celsius, lead crystals will start to form, increasing the cohesion of the liquid alloy. At 252 degrees Celsius, the mixture will start to fully solidify, during which the temperature will remain constant. Only when the mixture has fully solidified will the temperature start to decrease again. Using a 10% antimony, 90% lead mixture delays lead crystal formation until approximately 260 degrees Celsius. Using a 12% antimony, 88% lead mixture prevents crystal formation entirely, becoming a eutectic. This alloy has a clear melting point, at 252 degrees Celsius. Increasing the antimony content beyond 12% will lead to predominantly antimony crystallization. Tripolar mixtures equals, adding tin to this bipolar system complicates the behavior even further. Some tin enters into the eutectic. A mixture of 4% tin, 12% antimony, and 84% lead solidifies at 240 degrees Celsius. Depending from the metals in excess, compared with the eutectic, crystals are formed, depleting the liquid, until the eutectic 4/12 mixture is formed once more. The 12/20 alloy contains many mixed crystals of tin and antimony. These crystals constitute the hardness of the alloy and the resistance against wear. Raising the content of antimony cannot be done without adding some tin too. Because the fluidity of the mixture will dramatically diminish when the temperature goes down somewhere in the channels of the machine. Nozzles can be blocked by antimony crystals. Metals used on typecasting machines equals, eutectic alloys are used on linotype machines and Ludlow casters to prevent blockage of the mold and to ensure continuous trouble-free casting. Alloys used on monotype machines tend to contain higher contents of tin, to obtain tougher character. All characters should be able to resist the pressure during printing. This meant an extra investment, but monotype was an expensive system all the way. Present usage of type metal equals. A fierce competition between the different mechanical typecasting systems like linotype and monotype has given rise to some lasting fairy tales about tip metal. Linotype users look down on monotype and vice versa. Monotype machines, however, can utilize a wide range of different alloys. Maintaining a constant and a high production meant a strict standardization of the tip metal in the company, so as to reduce by all means any interruption of the production. Repeated assays were done at regular intervals to monitor the alloy used, since every time the metal is recycled, roughly 0.5% of tin content is lost through oxidation. These oxides are removed with the dross while cleaning the surface of the molten metal. Nowadays this battle has lost its importance, at least for monotype. The quality of the produced type is far more important. Alloys with a high content of antimony, and subsequently a high content of tin, can be cast at a higher temperature, and at a lower speed and with more cooling at a monotype composition or supercaster. Although care was taken to avoid mixing different types of type metal in shops with different type casting systems, in actual practice this often occurred. Since a monotype composition caster can cope with a variety of different metal alloys, occasional mixing of linotype alloy with discarded typefounders alloy has proven its usefulness. Mechanical line casting equipment use alloys that are close to eutectic. Contamination of type metals. Copper has been used for hardening type metal. This metal easily forms mixed crystals with tin when the alloy cools down. These crystals will grow just below the exit opening of the nozzle in monotype machines, resulting in a total blockage after some time. These nozzles are very difficult to clean, because the hard crystals will resist drilling. Zinc. Brass spaces contain zinc, which is extremely counterproductive in type metal. Even a tiny amount less than 1% will form a dusty surface on the molten metal surface that is difficult to remove. Characters cast from contaminated type metals such as this are of inferior quality, the solution being to discard and replace with fresh alloy. Brass and zinc should therefore be removed before remelting. The same applies to aluminium, although this metal will float on top of the melt, and will be easily discovered and removed, before it is dissolved into the lead. Magnesium. Magnesium plates are very dangerous in molten lead, because this metal can easily burn and will ignite in this way the metal in the pot. Iron. Iron is hardly dissolved into type metal, although the molten metal is always in contact with the cast iron surface of the melting pot. Historic references to type metals. Joseph Moxons, in his Mechanic Exercises, mentions a mix of equal amounts of antimony and iron nails. The antimony here was in fact stibnite, antimony sulfide. The iron was burned away in this process, reducing the antimony and at the same time removing the unwanted sulfur. In this way ferrosulfide was formed, that would evaporate with all the fumes. The mixture of stibnite and nails was heated red hot in an open-air furnace, until all is molten and finished. The resulting metal can contain up to 9% of iron. Further purification can be done by mixing the hot melt with kitchen salt, NaCl. After this red-hot lead from another melting pot is added and stirred thoroughly. Some tin was added to the alloy for casting small characters and narrow spaces, to better fill narrow areas of the mold. The good properties of tin were well known. The use of tin was sometimes minimized to save expenses. Much of this toxic work was done by child labor, a labor force that includes children. As a supposed antidote to the inhaled toxic metal fumes, the workers were given a mixture of red wine and salad oil. References